In this example, we're given an RL circuit that has one inductor, a bunch of sources and resistors. So basically it's a first order circuit. And what we're being asked to compute is the following, the current flowing through it. So if you take a look at it, we're going to assume that the switch has been at A for a very long time, and then at some point, which is time equals 0 or t equals 0, we'll basically switch it to B, and we're going to find the current flowing right before it and afterwards, basically for t is greater than 0. Actually, it's greater than or equal to 0, it's the same. And also we're going to see what the initial voltage across it, and we'll solve another exercise in here, which is basically to find the voltage across 24. So let me get started, and the way I'm going to do it is, well, what we have is we have a couple of circuits right before switching and right after switching. So let me just draw these. So right before switching, it appears something similar to that. That's before switching. Okay, so this is 8 amps, okay, and that's 10 ohms, and this is basically 200 millihenries. And if you think about it, if we wait in A for a very long time, this source is a DC source. So technically, this 200 millihenries is just simply a wire, and the voltage across is 0. And because of that, that means there's no resistor in here, because this resistor is basically shorted out. That means the current that is actually flowing through 8 amps in here is actually flowing that way. So technically, the current flowing through that in here is just simply 8 amps, and I'm just going to call it I0 because this will be the initial current flowing through that inductor right when we switch, because before switching it was I0 happened to be 8 amps, and right after switching it will still be 8 amps because inductors oppose a change in current. Alright, so we have now the initial current. I'm going to call it initial is just because at t0 that will be the value of that inductor. Now right after switching, we'll end up with a particular circuit that looks something similar to this, which is 24 in here, volts connected to 2 ohms. And then what we have is we have right after switching, we have the inductor, which is 200 millihenries, okay, and which is 200 millihenries, yes. Okay, and what I will say is the I0 with this particular direction is 8 amp, and what I'm interested in is actually that here is VL of t, and I'm also interested in this current actually flowing this way, which is IL of t. I'm interested in both of them. Now, we do have some equations, we've seen it. This is just a simple step response of an RL circuit, and these are the equations that describe it, but these equations do not describe this circuit. What they describe is the following. They describe a circuit that is basically a Norton equivalent, and this here is inductor. Okay, so we'll have some sort of an R in here, and we'll have an L in here, and so forth. And to be more specific, what we did is we assumed that the I of S happened to be in this direction, okay? And we assumed that that was V of L of t, and that's basically IL of t. So these are the assumptions we had when we found these two equations in here. Okay, so let's double check what we have in here. Well, what we have is we have the Thevenin equivalent in here, and instead the equations we derived were based on Norton equivalent. So we can either compute Norton, we can simply do source transformation on these two here, which is the voltage source and the resistor, and we'll get the Norton equivalent. So let me just do that. So I'll redraw the circuit after switching and using just the Norton equivalent. So that will be a current source in parallel with the 2 ohms. Okay, and that will be in parallel with a 2 millihenry or 200 millihenries inductor. Okay, and that inductor will have this particular one, which is I0 is simply 8 amps. Okay, and the current I'm interested in is this current in here, which is IL of t, and the voltage across it, which is VL of t. The current source in here is just simply 24 divided by 2, which is just simply 12 amps. That's basically the current source that we have, and that's basically my I of S, which is 12 milliamp. All right, so now all we have to do is just basically substitute. So what we need is IL of t equals I of S, which happened to be 12, plus I0, which happened to be 8, and I of 8, well, let me just make sure that we have it in here. Well, I0 in this particular case, we assume that I0 in here is that way, okay, but now we know that I0 is not this way, it's actually the opposite. So what we have is we have to substitute it by negative in here, okay, because the I0 is in the opposite direction of I of L. That's what we have, okay. All right, so we can do this, negative 8, negative I of S, which is 12, e to the negative 1 divided, well, what's the tau? Well, tau is just simply L divided by R, which is just simply 200 times 10 to the negative 3, because that's in millihenries, and the R happened to be 2 in this particular case. This is the R that I should be focusing on. It's the same R as in here, and that basically is just simply, I believe it's 100 milliseconds. okay, or maybe you can think about it as 100 times 10 to the negative 3 seconds. Okay, so 1 divided by tau is just simply 10 seconds to the minus 1, basically, because it's reciprocal. So this becomes negative 10 of t minus t0, and t0 is just 0. And that will be in amp for t is greater than or equal to 0. So we were able to find it, but let me just do a little bit of algebra just to clean it. We'll have 12 negative 20 e to the negative 10 of t. That's an amp for t is greater than 0. That's IL of t. And that's basically the equation for the current flowing through this particular inductor. And let's do a quick sanity check. At t equals 0, which we know right before and right after, we should get negative 8. So if you think about it, t equals 0, e to the power 0, that's a 1. So that leaves me with 12 minus 20, which is negative 8, which is exactly what we have in here, because the current actually, this is the I of t, and what you're telling me is initially we'll have a negative 8. And at infinity, let's assume that t is infinity. That means the whole thing here goes to 0. That means we'll end up with 12. And if you think about it, that here 12, actually this will become like a short circuit in here. Okay, this becomes a short circuit, so this will be shorted out. So this current in here will basically be flowing in here, and that will be exactly 12 amps, and that's what we have in here. So that's good. So now what we need to do is we need to find out what VL of t. And again, what we can do is you can either just tell me, well, it's L times di of L of t divided by d of t. And using passive sign convention, we'll see that this here is a positive, so we just use positive in here. Or you can just use the equation, which I will do. So the equation tells me this equation in here, okay? So the equation tells me what we do is negative r, which is negative 2, I0, which happened to be negative 8, minus I0. Why is it negative 8? Again, because I assumed that I0 is in the same direction as I of L in these equations, and I got it in the opposite direction. So I'll have to have negative 8, negative I of S, which is 12, e to the negative 10 of t. Okay, so we'll do the algebra in here. What we get is negative 20 times negative 2, what becomes 40, e to the negative 10 of t. That's VL of t, that's a function of t, and that's in volts, and that's for t is greater than 0, exactly greater than 0. Okay, so quick sanity check at t equals 0. Well, we know that right before switching it was 0, but right after switching it doesn't have to be 0. So right after switching we'll figure out that it's actually when you substitute t equals 0, it will be 40 volts. Okay, and I'll plot all of these for you. And at infinity, we'll see that that voltage becomes 0 in here because this becomes a wire at infinity, at time equals infinity. So we have those right, so let me just highlight it in here. All right, so what we have found is the current and the voltage across this inductor in here. That's what we have found. We were being asked to compute the current in here, we did. And now what we need to do is we need to figure out the voltage right before switching, right after switching. I said right before switching was 0, right after switching we just substituted 0 in here. And by substituting 0 we got 40 volts. So I can write those for you. So let me just do this here. So what we can do is we can say VL for 0 minus, because it was a wire, it's a 0. V of L right after switching is just simply 40 times e to the power 0, which is 1 volt. That's what we have. All right, so what's left? Well, what's left is to find the time at which, in millisecond, that V of L will become 24 volts. Basically, we know, well, why don't I just plot it so that I can explain it graphically speaking, what am I asking you to do? So what we have is in here, we have this is T, this is here. And initially, and let me just do this here. Initially, let me draw the current, and I'm going to just say this is IL of t. So the current initially, you'll see that it was when I of 0, we get negative 8. So initially, the current was here, which is negative 8 amps. And finally, when this t goes to infinity, so the whole thing goes to 0, so that becomes 12. So it will eventually go to 12 amp. And you'll see that initially we start at negative 8, and exponentially speaking, it will basically reach that negative 12. That's what happens. And there's a point at which the current will become 0, and we can compute it. Just you set this to be 0, and you figure out what that t is. And similarly for the voltage, you will see for the voltage that in here, okay, so the voltage initially, right before switching, it was 0. Right before switching. And right after switching, it actually jumped all the way to, let's assume that this is here is 40 volts. And they're not on the same scale. So VL of t is not on the same scale. And what you have is eventually it will go actually to 0. That's what we have in terms of voltage. Okay, so the current doesn't actually jump. So the current right before switching in here, if I'm actually to plot the current was basically at -8, it's stable, and then slowly it doesn't jump to a specific value, but the current does flip, well, the voltage does flip. Now, what we're being asked to compute to say, well, okay, so at what time that V of L will become 24 volts right after switching? So how long do I need to wait for that to be here? So we started at 40 volts, and what I'm asking you to say, well, let's assume that 24 volts is somewhere around here. This is the 24 volts. I'm asking what time that you see in here. It might, well, they're not per scale, so they don't have to be in the same time. Okay, but at what time does actually this happen? So all I have to do is just basically say VL, well, we know what VL of t, it is actually 24. That's what we're looking for, equals 40 e to the -10 of t. And hopefully you'll figure out that this t is about, I believe, 51.08 milliseconds. That's what I think. That at that particular point, it'll be 0. And we can compute exactly at that particular moment, we can compute how much the current will be by just substituting that. I can just tell you at I of L at 51.08 times 10 to the -3, because you have to substitute in terms of second, and that will be equal to 0 amp. So I got lucky with the drawing. It wasn't intentional, but I got lucky. I guess my drawing is very accurate, and we got exactly that. This is actually the point at which the current happened to be 0. So by saying like, hey, substitute this by 0, you'll end up with the same exact value.